How to solve recurrence equation? Recurrence equation. Earlier we have seen recurrence equation when we are dealing with the merge sort example, right? So in the merge sort example, what's the recurrence equation? So f of n is 2 times f of n by 2 plus n. So this is a recurrence equation. So you see the function is represented by itself. Okay. So it's this kind of equations called recurrence equation. Anyway, for this recurrence equation, we have seen how to solve it, but that kind of technique may not be possible in all the cases. There are several techniques available to solve the recurrence equation. Anyway, it is not fully there in your syllabus, and hence, I mean, wasting a time because that will take another 4 to 5 classes. Anyway, that's not good. But I am giving you a best method of solving it. That is called the algebraic method. I think for your syllabus that would be sufficient because most of the analysis, whenever we are getting the recurrence equation, we can straight away apply that and get it, no problem. Okay. And though there are several methods, why there are several methods? Because some recurrence equation that can be solved using certain methods, but other method may not be possible. Okay, so different. Even if I explain all the methods, still there are some recurrence equation, and we have to apply some tricks so that that can be converted in some other form and then solved. Okay, so that's a difficult thing. So for you, anyway, you are currently that semester, and anyway, this is not fully covered in your syllabus. I am giving only one technique, that is solving recurrence equation using algebraic method, and that is sufficient. Okay, that is sufficient for your complexities that we discussed later part of this course. Okay, the recurrence equation in general, how we can write is recurrence equation is of two kinds. The one is called the homogeneous recurrence equation, other one is called the inhomogeneous recurrence equation. So recurrence equation that can be, it is not non-homo. We are not saying non-homogeneous, but better word is inhomogeneous. So homogeneous recurrence equation are inhomogeneous because in the inhomogeneous, the homogeneous recursion is inside. It will be available. So the term inhomogeneous is commonly used in the algorithmic study. In some mathematics books, they may use the term called non-homogeneous. Okay, no problem. But understanding of the equation, that is sufficient. Okay, first let us take a homogeneous recurrence equation. So homogeneous recurrence equation can be described in general. That is T of n is equal to some B1 T n minus 1 plus B2 T n minus 2 plus etc. plus BK BK T n minus K, like that. Okay. So why we call homogeneous recurrence equation? This is homogeneous recurrence equation. The reason is if you move, because in the right hand side, if you look at the right hand side, left hand side, the function is t, right? The right hand side also, the terms are having t, the function t. So here t is there, here also like that. So if you bring that function t terms, okay, to the left hand side. So all the terms that containing the function t, if you bring it to the left hand side, what will be at the right hand side? Because this is having this one. So this will be brought here, and this also like that. This also to be brought here like that. So right hand side will be 0. So homogeneous recurrence equation, if you bring, okay, if you bring all the terms containing the function to one side, the other side will be having value 0. Other side, you will be having only value 0. Okay, now if I bring that, this becomes, I can write like that, that is A0 T of n plus A1 T n minus 1 plus etc. plus AK T n minus K. So that is equal to 0. Anyway, you may ask that we have B1, B2 there, why we get A0, A1 like that? No problem. Anyway, these B1, B2 are constants. Okay, I have replaced the constant with another variable that is called A's. Okay. Now you see A0 equal to 1 and A1 is equal to minus B1 and A2 equal to minus B2 like that. Okay, so that way I replace those constant value with some other one, right? Okay, no problem. Anyway, we want only the general terms. So now your homogeneous recurrence equation. Now once you brought all the functions to the one side, what happened? Right hand side is equal to 0. So this is the homogeneous recurrence equation. Now, what we have to do is we have to convert into a polynomial. Okay, we have to convert into a polynomial. I think you might have studied polynomials, right? So, if you are converting into a polynomial, what we do is these functions should be converted. These functions should be converted into a variable with some exponent. Then it becomes a polynomial. So to convert this into a polynomial, what we do is let t of I is equal to, t of I equal to x power I. So if we substitute that. So if you do that, what you get? You get a0 x power n, right? So we are substituting like this. a0 x power n plus a1 x power n minus 1 plus etc. plus ak x power n minus k, that is equal to 0. Okay, now you got a polynomial. This polynomial having common terms. What is the common term? So x power n minus k is common. So if you take it out in your right hand side, the 0 there, therefore that can be removed, right? So common terms can be removed because right hand side 0 is there. So if I remove that constant term, what you get? You get a0 x power k plus a1 x power k minus 1 plus etc. plus ak that is equal to 0. So we got a polynomial of degree k, polynomial of degree k. So if you solve this polynomial, if you solve this polynomial, you get roots of the polynomial. Okay, you get the roots of the polynomial. As the degree of the polynomial is k, how many roots will be there? If a polynomial having degree k, how many roots will be there? K roots, right? K roots. You get k roots. So, but we do not know what the roots are. So the roots may be, some of the roots may be same, or all the roots may be same, or all the roots may be distinct. We do not know. So the first case, what you assume is, what we assume is all the roots are distinct. So let the roots be k1. Let the roots be r1, r2, etc. rk. There are k roots. Let the roots be r1, r2, etc. rk. Okay. First case, we assume that all the roots are distinct. That is, we can say that ri not equal to rj for all I not equal to j. Okay. That means all the roots are distinct, right? So if it is not in the focus, just tell me because I may not note this sometimes. Okay. So first case is all the roots are distinct. So no two ri's are same, right? So that's what we assume. If all the roots are, otherwise we can write all the roots are distinct. All the roots are distinct. So in that case, the general solution of the polynomial is, because t of n is our polynomial, right? T of n is equal to, we can write that as sigma I is equal to 1 to k ci ri power n. So even the k roots, there are k roots. So sigma I equal to 1 to k. This is a general solution. So from the general solution, we can find a particular solution. That is, if you have the initial condition, based on the initial condition, you can derive the constants. You can find the constants, and if you substitute that, you get the particular solution. This is what we do in the polynomial, even in the differential equations like that. But here that is not required for us, because anyway we are going to take the asymptotic value. So general solution is more than sufficient. Okay. So and again we can stop with the general solution. Anyway, this is common, but particular solution when we get this, when we take some examples, we can get. That is possible, but it is not necessary for us. And again, so we can stop with general solution. Then what happens is, for example, if you have the polynomial, that polynomial is actually called the characteristic polynomial. Okay, so that is given a recurrence equation. Already we have seen that given a recurrence equation, how the recurrence equation will be converted to a polynomial, and we usually say that the polynomial is a characteristic polynomial. And if we assume that the characteristic polynomial of a recurrence equation is something like that, anyway, we are not writing the equation, we are straight away, because we have to explain you to how to find the complexity. Okay, the polynomial is like x square minus 5x plus 6, that is equal to 0. It's a homogeneous recurrence equation. So actually the equation will be something like that. So you might have the t2, okay, we may have tn. So actually the polynomial, anyway, I can explain you first time, so that will be better. So polynomial will be something like t of n, that is equal to phi t of n minus 1, okay, n minus 1 plus 6 t n minus 2. So this is the recurrence equation you have. So if you convert into a polynomial, what you do? You put x power n is equal to 5. So this is minus, okay, minus. Okay, 5 x power n minus 1 minus 6 x power n minus 2. So if you bring this to the left hand side, what you get? X power n minus 5 x power n minus 1 plus 6 x power n minus 2. So that is equal to 0. So if you remove the constant term, you get x square minus 5x plus 6, that is equal to 0. So this is what I have written here already. So anyway, just to reduce the time, I straight away written the characteristic polynomial, because you should know that once you have the polynomial, how to write the complexity. So if that's the case, what do you get? Your complexity will be t of n is equal to, according to this formula, there are, so okay, here the factorization is, you have to find the roots, right? Factorization is, it will be x minus 3 into x minus 2, right? X minus 3 into x minus 2. Because sum is minus 5 and product is 6 plus 6, right? So you get two factors. So this is 0. That means values of x are 3 and 2. Now these are the roots. Roots are distinct. So if the roots are distinct, you can use this formula. Okay, if the roots are distinct, you can use this formula. So what will be your t of n? T of n is equal to, according to this formula, c1 into 3 power n plus c2 into 2 power n. Okay, now you see that 3 power n, 2 power n, both the things if you compare, 3 power n is larger. So you can say that this is equal to order of 3 power n. So the algorithm which is having the recurrence equation, something like that, its complexity will be order of 3 power n. We can see the second case. So that is case 2. So suppose the roots are not distinct. Suppose the roots are not distinct. So we can assume that first p roots are same. Okay. We can assume that the first p roots are same. So if the first p roots are same, and we assume that remaining roots are distinct. Okay. So if the first p roots are same, then the solution is t of n is equal to sigma I is equal to 1 to p. So first p roots, right? I is equal to 1 to p. Then Ci. So for the same roots, okay, first p roots are same. That's our assumption. So for the same roots, the solution will be like that: Ci, then n power I minus 1. Sorry, n power I minus 1. Then Ri power n. Okay, if the roots are same, this is the format you have to take. If the roots are distinct, then the earlier one should be considered. Okay, so first p roots are assumed to be same, and again for p roots, this is a general solution. And for the remaining roots, anyway, that is distinct. So that we can write I is equal to p plus 1 to k. So there are k roots, right? So remaining roots that are distinct. And for that roots, we can write Ca Ri power n. So like something we have written earlier. Okay. So now we assume we can take one example. We assume that our characteristic polynomial is like that. X minus 3. Anyway, after simplification, I am giving. Anyway, you know that how to convert into polynomial and factorization, everything. So I am giving it in the factorized form. So x minus 3, okay, I can say, I take this side. Okay, suppose the polynomial is x minus 2 power 3, then x minus 3, that is equal to 0. Now, if you solve this polynomial, what are the roots? So here power 3 there. Therefore, x minus 2 equal to 0 means 2 is the root. So there are 3 times it appearing, right? So roots will be 2, 2, 2. So first three roots are same. Then the root is 3. So what we can do? Then we can write the general solution. What the general solution says that? So general solution says for the common roots. Anyway, I think you have noted down the formula, right? So anyway, I can write once again here. So that is sigma I is equal to 1 to P Ci n power I minus 1 then Ri power n. So this is for common roots, and for the distinct root, that is I equal to P plus 1 to K, that is Ci Ri power n. So here for the first P roots, here first three roots, right? We have to use this form. So we can say that this is equal to this summation. When I is equal to 1, what we get? We get C1 n power I equal to 1 means n power 1 minus 1, 0. Okay, the n, this term won't come. This term won't come. So C1 2 power n, then plus C2, second time it is I equal to. So n power 2 minus 1. So that is n power 1 n. Okay, so n into 2 power n. And the third term it will be C3 n square 2 power n. Okay, now you see n power 0, n power 1, n power 2 like that. So the other one is the R power Ri power n. That will be the same because same roots, right? 2, 2, 2 like that. So if three roots are common, then it will be coming like that. Three terms will be coming. Then next one is this one. So that is C4. So fourth root, that is 3. So C4, 3 power n. 3 power n. Okay. So now you see this is what the solution. This was the solution. Okay, now if you compare this and this, anyway, this term n 2 power n is larger than this, then n square 2 power n is larger than this. Okay, but only thing is confusion is between these two, whether this is larger or this is larger. So anyway, here 2 power n is exponential function, here 3 power n is exponential function. But here what happens is apart from 2 power n, there is one more value available, that is n square, right? We are multiplying by n square. But actually we have to take the asymptotic value. We have to take the asymptotic value. So when n is large, automatically this becomes larger, right? This becomes larger. So we can say it is order of 3 power n. So that's the complexity. Okay. Now we can take two more examples. Suppose we assume that the recurrence equation is given as T of n is equal to 4t n minus 1 minus 3t n minus 2. Okay, suppose the recurrence equation is given like that. Then what you have to do, you have to convert into a polynomial. So if you are converting into a polynomial, I can write straight, but for the clarity for you, okay, I am writing some steps. So to convert into a polynomial, we can say this is x power n, that is 4x power n minus 1. And minus 3 x power n minus 2. So this is what we get. Now we can bring everything to the left side, all the terms containing x to the left side. So this implies x power n minus 4x power n minus 1 plus 3x power n minus 2, that is equal to 0. Now if you remove the common terms, what do you get? You get x square minus 4x plus 3, that is equal to 0. So if you factorize it, what do you get? You get x minus 3 into x minus 1, that is equal to 0. So the roots are, okay, so the roots are 3, 1, but the roots are distinct. And hence we can say the complexity is T of n is equal to C1 3 power n plus C2 1 power n. So okay, compared to these two, 3 power n is larger. So we can say it is order of 3 power n. We can say it is order of 3 power n. Okay, so this is a way how to solve that. So one more example we can take. Suppose the recurrence equation is like that. T of n, that is equal to 4t n minus 1 minus 4t n minus 2. So now in this case what happens if we convert into polynomial x power n equal to 4x power n minus 1 minus 4x power n minus 2, right? So you can bring everything to the left side. So x power n minus 4x power n minus 1 plus 4x power n minus 2, that is equal to 0. So what you get? So if you remove the common terms, you get x power 2 minus 4x plus 4, that is equal to 0. So this implies if you factorize, you get x minus 2 into x minus 2 equal to 0. So the roots are 2 comma 2. So roots are same. So if the roots are same, then what happens? Tn is equal to c1 2 power n plus c2 n 2 power n. Okay, if the roots are same, what to be used, that we have discussed. Okay, so you get this. So this is equal to order of, this is larger, right? Order of n 2 power n. Order of n 2 power n. Okay, so this way you have to find that. Okay, now the question is, anyway, we have discussed first p roots are same. So like that, first p roots are same, then next q roots are same, like that. So wherever the roots are same, you have to use that particular. For example, first p roots are same. Similarly, next q roots are same. Then remaining thing is distinct. Then how your recurrence equation, the T of n is equal to sigma I is equal to 1 to p. Okay, Ci n power I minus 1. Okay, n power I minus 1. Then Ri power n. Then for next q roots, so that is equal to sigma I is equal to p plus 1 to p plus q, right? P plus q, next q roots. So for that it is again Ca n power I minus 1 Ri power n. Okay. Okay, but this Ri will be different, this Ri will be different. Okay. So these Ri's are common and these Ri's are common. Then for the remaining roots, it will be sigma I is equal to p plus q plus 1 to k. We will be having the, distinct root formula, right? Ci Ri power n. So like that. So depending on the common root, whenever common roots comes, you have to use this. Okay, the multiplied by some n power is required. If the roots are distinct, that multiplication of n power something won't come. Okay, so that if you remember that, that would be sufficient. So this way you can solve that. This is for the homogeneous recurrence equation. But what happens is sometimes our complexity, the algorithm complexity will be inhomogeneous. So the general format for the inhomogeneous recurrence equation is, maybe you have the okay, I can write here inhomogeneous. Okay, the equation will be of the form a0 tn plus a1 tn minus 1 plus etc. plus ak tn minus k. Then that is equal to, that is once you bring all the terms containing the function to the left side, other than 0, something else will be there. Okay, so that is called inhomogeneous. Okay, so that is equal to the right hand side. Okay, the space is not there, that's why I am writing here. Actually this is a single equation. Okay, so that is equal to, don't assume that the equal to is coming from this. Any other is, I can write one term here. So I can say b1 power n, b1 of n, then plus b2 power n, b2 of n plus etc. Like that, any number of terms will be there. So 0 is not there, the right hand side, right? So this is inhomogeneous recurrence equation. Why we say that is, this equation is having so many homogeneous equations. Okay, so we can split into a collection of homogeneous equations. So the homogeneous equations are, one is corresponding to the left hand side. So left hand side, if you consider left hand side is equal to 0, you get something, right? So for example, if you take left hand side is equal to 0, what you get? You get a0. Okay, and this can be converted into polynomial, right? So a0 x power n plus a1 x power n minus 1 plus etc. plus ak x power n minus k, that is equal to 0. And if you remove the terms, what do you get? Remove the common terms, what do you get? a0 x power k plus a1 x power k minus k minus 1 plus etc. plus ak, that is equal to 0. So degree of the polynomial is k and its k roots come. Okay, so if you consider that the set of homogeneous equation is one corresponding to the left hand side, so that is a0 x power k plus a1 x power k minus 1 plus etc. plus ak, so that is equal to 0. So this is one equation. Now we can also, This is not visible, huh?
Yes, sir, it's not.
Yeah. So one corresponding to the left hand side. Okay. So this is A0 x power k plus A1 x power k minus 1 plus etc. AK equal to 0. Then remaining thing is corresponding to the right hand side. Okay. Right hand side first term. Anyway, I think you have noted down or not. Okay. Better I can write the equation here. A0, the given inhomogeneous equation is A0 T of n plus etc. plus AK T n minus K. So that is equal to B1 power n, P1 of n plus B2 power n, P2 of n plus etc. Like that any number of terms will be. So this is corresponding to the left hand side. And for right hand side, first we can take this particular term. Okay, right hand side, we can take this particular term. For this term, the homogeneous equation is x minus b1. b1 is a constant. b1 is a constant. So some constant power, the size of the input will be there, right? N is the size of the input. Some constant power, the size of the input. So if that's the case, the constant should be taken here. So it will be x minus b1, then power d1 plus 1. So what is d1? d1 is degree of the polynomial p1 of n. So here p1 of n is the polynomial. So apart from the constant power, the size of the input, some polynomial will be there. So we have to see the polynomial degree, and the degree plus 1 should be the power of this homogeneous equation. So that is 0. That is another homogeneous equation. Similarly, if you take the second term, so there you get x minus b2 power d2 plus 1. So that is equal to 0. Once again, b2 is a constant and d2 is the degree of this particular polynomial. So like that, depending on the number of terms, you will be having the set of homogeneous recurrence equation. Now, if you solve this homogeneous equations, anyway, here k roots will be there, right? K roots will be there. Here, anyway, d1 plus 1 roots are there, but all the roots are b1. Okay, x minus b1 is equal to 0, like that, right? So all the roots are b1. Here, all the roots are b2, but number of roots are d2 plus 1. So here some set of roots there, here some set of roots there, here some set of roots there. Now you have to take S is equal to union of all that, S1 union, S2 union, etc. So union all that. So this will be the solution set. Now in the solution set, based on the solution, if it is distinct or some roots are same, whatever we have done in the previous case, the formula to be applied for the general solution. So we will get the answer. Okay. Now only thing is you have to convert something into this, then get the roots. Then after that, whatever we have done in the homogeneous case, that can be considered, right? Okay, now we can take inhomogeneous recurrence equation. Already we have seen the complexity for merge sort. So the function is like that. Recurrence function is like that. F of n is equal to 2 times f of n by 2 plus n. So this is the complexity for merge sort. Okay, now to solve that, anyway, the fraction is that first of all we have to remove the fraction. Therefore, we are taking let n is equal to 2 power k. So if you put n is equal to 2 power k, why we want to do that is because directly we cannot apply this. So these formulas are saying that t of n minus 1, t of n minus 2, something like that. It is not like n by 2 like that, right? So we have to bring it to that particular format. So if you bring it to that particular format, then only we can apply, right? So to bring it to that particular format, we are substituting n is equal to 2 power k. So if you put n is equal to 2 power k, what happens? This is f of 2 power k. So that is equal to 2f of 2 power k minus 1 plus 2 power k. Now what happens is you see k minus 1 format come, but it is not straight. So once again we are saying that let t of n is equal to f of 2 power n. Okay, so if you use this, then what happens is this implies this is t of k that is equal to t of k minus 1, right? K minus 1 plus 2k. So when this is only changing the things, okay, it is only for you to understand. Otherwise, you can straight away do that. Okay, I am taking only the power. Power is something like k minus 1 like that. So I am converting into something this particular format, but here it won't be changed because variable is not changed. Okay, variable is not changed. So if I do that, first what I have to do in the inhomogeneous recurrence equation, I have to bring all the terms containing the function to the left hand side, right? Then something else will be at the remaining side. So now here what happened? This is the term containing t. So that can be taken to the left side, but this cannot be. So if I do that, what I get tk minus 2 times tk minus 1 equal to 2 power k. Okay. Now you see right hand side is not 0. So it is an inhomogeneous recurrence equation. So we have to convert into set of homogeneous equation. For the left hand side, once you make the substitutions and other things, what you get is, for left hand side, what you get is x minus 2 equal to 0. That's all, because only two terms, x minus 2 equal to 0. Okay, once you practice, you can straight away do that because by seeing that, what I have done is, anyway, if I convert the polynomial and other things, anyway, common term will be removed, only this 2 will be there, the next term will be x like that. So x minus 2 equal to 0, straight away I have done. Okay, now for the RHS, right hand side, so here the format is something like b1 power n, p1 of n, right? So b1 is a constant. Here what is a constant? 2 is a constant. What is our k? K is our size of input because n is converted into something in terms of k, right? So as of now, k is our size of input because we converted. Okay. So k is our size of input. Therefore, b1 power k. So this is our b1. This is our size of the input. Then polynomial p1 of n. So nothing is there. So that is equal to 1. So if nothing is there, you can consider multiplied by 1, right? So this is right hand side once again x minus 2. The solution is x minus b1 here, right? So x minus 2 power degree of the polynomial plus 1. So here polynomial is 1. It's a constant polynomial. So degree of the constant polynomial is 0. Degree of the constant polynomial is 0. So 0 plus 1, 1. So the x minus 2 equal to 0. This is for right hand side. So here what you get, the solution is 2. Here the solution is 2. There are two roots, 2 comma 2. So roots are same. So if the roots are same, what will be your this thing? Okay, t of k. Okay. Anyway, now the variable is k. With respect to k, only we have done. So we have to write t of k. We have to, sorry, t of 2 power k. Okay, t of 2 power k. So that is equal to c1 2 power n. The roots are same, right? So c2, sorry, k. Variable is k, right? c1 2 power k plus c2 k 2 power k. The size of the input is now k. So therefore we are using this, right? But what do we want? We want the value in terms of n because in original thing n is the size of the input. So we have to substitute it to back. So if you put n is equal to 2 power k again, so this implies t of n, right? N is equal to 2 power k. So that's why it is t of n and c1 this 2 power k is n and plus c2 this 2 power k is n but k is equal to log n, right? So it is n log n. So what is log n? This is log n. So that is equal to order of n log n. But what happens? We applied some condition. So when n is a power of 2, right? N is a power of 2. So that's a conditional probability. Sorry, it's a conditional asymptotic notation. Sorry, conditional asymptotic notation, right? But we have already seen that how to remove the condition for this particular example. Already we have proved. Okay, therefore, what we can say is we can straight away write order of n log n. Otherwise, we cannot. Therefore, whenever such conditions are being applied and you are being asked to find the complexity, you have to write the complexity and the condition should be there. Unless otherwise, you prove it. Okay, so you have to say like that. But in this case, why we are doing is already we have done it. That proof already we have done, right? And against we have removed. Otherwise, you should not remove that. You can write something like this, right? Something like this. Okay, we can take few more examples. The next example is suppose the recurrence equation. Some problems we can see. Recurrence equation is given like t of n minus 2t n minus 1 equal to 3 power n. T of n minus 2 t minus 1 equal to 3 power n. Anyway, already all the terms containing t or the function is at the left hand side, right? So that part is not required. And right hand side is not 0, but some constant power size of the input that is available. Okay. So anyway, this is already in the required format, so nothing to worry. We can straight away do that. So set of homogeneous, one is corresponding left hand side. So left hand side what you get? X minus 2 equal to 0. And right hand side what you get? Here constant is 3, right? So you will get x minus 3 and into 1 actually. Polynomial is a constant polynomial. So x minus 3 per 1. So that is equal to 0. So roots are 2 and 3. Therefore what you get? The T of n is equal to C1 2 power n plus C2 3 power n. So that is equal to order of 3 power n. So that's all. Okay. So how do we get this recurrence equation? That is based on the problem logic. Maybe the merge sort. We have seen the logic of how to solve it, and based on that we got the recurrence equation. Okay, one more problem I can consider so that you get the idea how the recurrence equation comes. Okay, whenever the problem is having the recursive nature, then the recurrence equation will come. Accordingly, maybe you may have the recursive algorithms also. Another problem is called the Tavra-Hanay problem. I don't know whether you have studied this problem in your problem solving techniques. I don't know. So Tavra-Hanay problem. So Tavra-Hanay problem is like that. There are 3 pegs. Okay. So this is peg A, peg B, and peg C. Now our assumption is here we have n disk. Okay, it is something like a rod, and the disk is having the hole, so we can put the disk one by one. But how we put that is the larger disk at the bottom, then next smaller one, then next smaller one, next smaller one, like this. Okay, so this is the input. So here we assume that there are n disks. Here there are n disks. So the problem is like that. Here the peg A containing n disk arranged according to the size. But you see, if you want to remove a disk, only the top of the disk can be removed because it is already been put inside the. The rod is inside, right? So we cannot remove the disk from the middle. So you can take only the top one. You can take the top one and place it. Okay, the problem is like this. Here n disk are available. This n disk to be moved to peg C using BS auxiliary. Using BS auxiliary. This can be used for temporary. But at the end, all the n disks should be moved to C, provided. Once again, here also that should be in the decreasing order, decreasing size. Similarly, whatever the order here maintained, the same order disk should be in C also. So how we solve the problem is, what I can do is, first of all, I can move the n-1 disk, so except the last disk. Okay, I can move the n-1 disk to B. Okay, so to B using CS auxiliary. Using CS auxiliary. Okay, and after that I can move the nth disk to C. Okay, this disk to this one. Then here n-1 disk there, this n-1 disk can be moved to this one using AS auxiliary because A is empty now, right? A is auxiliary, so that I get the problem gets solved, right? The problem gets solved. Okay, so here we can apply the recursive algorithm. Accordingly, if you write the complexity, suppose T of n is the complexity of solving Tavra-Hanay with the n disk. Okay, Tavra-Hanay with the n disk. Then this is considered like, so how we are doing, 2 times we are moving n-1 disk. One time n-1 disk from this to this, then this to this. So 2 times of complexity of solving the same problem with the size of the input n-1. And apart from that, we are moving one disk to this place, right? So that plus 1. So n-1 here, so n-1, then one disk to this one, then another n-1, so that again. So 2 times t n-1 plus 1. So what we got? We got the recurrence equation. Now let us see the complexity of this problem. So this is, first we can bring all the t terms to the left side. So this implies t of n minus 2 times t of n-1, that is equal to 1. Now you see right hand side is not 0. So this is an inhomogeneous recurrence equation. So if you convert into a homogeneous set of homogeneous equation, for left hand side what you get is x minus 2 equal to 0. Then for right hand side it is 1. So it is, that is equal to something like 1 power n into 1, right? So constant power n then into 1. So that is x minus 1 degree of the polynomial is 0, so x minus 1 power 1, so that is equal to 0. So roots are 2 comma 1. The roots are 2 comma 1, roots are distinct, and against the t of n. Okay, t of n is equal to c1 into 2 power n plus c2 into 1 power n, which is larger. 2 power n is larger, so order of 2 power n. So this is a exponential complexity. This is a exponential complexity. Tavarahane problem is exponential complexity. Okay, you see, when we consider the algorithm, what kind of algorithm we are interested in is algorithm having the polynomial complexity. Why? Because exponential complexity in the sense, if the size of the input increases, the growth, okay, the time growth will be exponential. Okay, it's huge. We cannot say that we are always trying to solve the problem for smaller input. So we are looking at asymptotic way. Okay, so if the problem size is larger and the complexity is exponential, maybe to solve the problem it may take sometimes even so many days. Okay, so that is not good for. But some problems that cannot be solved in polynomial time. So this is what the study we do in the complexity theory. That's another huge topic. Okay, so we see only a little bit of complexity, but based on the complexity, there are collection of complexity classes and some theories are there. Okay, so anyway, we are not going to that, but the fundamental things we have to remember. So generally, when we say the algorithm is acceptable in the sense, if the algorithm is polynomial complexity, no problem. Polynomial in the sense it is n power c, right? C is a constant. So maybe complexity is like r of n or r of n square. Okay, then r of n log n. So log n is log n polynomial. No, it's not polynomial, but it is polynomial bound. It is having a polynomial bound. So because log n is always less than log n is less than n, right? So therefore, it is having a polynomial bound. So this detail we will see at the probably end of this course when we discuss about NP completeness. Okay, now you remember whenever the algorithm is having polynomial time, it's okay. If it's exponential, it's not good. But some cases we cannot get. Okay. Here one example, the Tavarahane problem, if we solve, the complexity is exponential. Okay, one more example we take. So let us assume that the recurrence equation is T of n is equal to 2 times T n minus 1 plus n 2 power n plus n square. Okay. So here first what we have to do, we have to bring all the t terms to the left side. So it will be T of n minus 2t n minus 1 and right hand side n 2 power n plus n square. Okay. You see right hand side is not 0. So it is inhomogeneous recurrence equation. So for the left hand side, what you get? Here you get x minus 2 equal to 0. And for the right hand side, two terms are there. So for the first term, constant power n. So that is x minus 2. N is the polynomial, right? N is the polynomial. So that polynomial degree is 1. So x minus 2 power 2 equal to 0. And one more term is there, that is n square. But n square into 1 power n. It is something like n square into 1 power n, right? So constant is 1. So x minus 1, but degree of the polynomial is 2. So 2 plus 1, 3. So x minus 1 power 3 equal to 0. So what are the roots? Here 2, here 2, 2, here 3, sorry, 1, 1, 1. So there are 6 roots. First 3 roots are same and next 3 roots are also same. Okay, 2, 2, 2, 1, 1, 1. So if you write the complexity, what you get? T of n is equal to C1 2 power n plus C2 n 2 power n plus C2 n square 2 power n for these 3. And for the remaining things, C4 1 power n plus C5 n 1 power n plus C6 n square 1 power n. Now if we compare that, this term is larger, right? So that is equal to order of n square 2 power n. So that's the overall complexity. Okay. Now let us see one little more difficult problem. In some cases it may come like that. So next problem. Suppose the complexity is like this. Recurrence equation is like this. T of n is equal to 2 into T of flooring of root n plus log n. Okay, now you see already we have seen when it is something like n by 2, how to remove the fraction. Okay, so we make some substitution and hence the fractional part will be removed. Then after that we can do that. So here it is something like root n. So this root n and flooring, ceiling, so everything should be removed before going for substituting in the algebraic method. So in this case, first we have to remove the flooring. Okay, we have to remove the flooring and root. So what we are substituting is let m is equal to log n. Let m is equal to log n. Then what happens if m is equal to log n? Then what is n? N is equal to 2 power m, because this is log to the base 2, right? N is equal to 2 power m. So what happens this equation? This is T of 2 power m equal to 2 times T of this is root n. Root n means n power 1 by 2. N is equal to 2 power m. So we can say 2 power m by 2. So automatically the flooring goes off. Why? Because this 2 power something is always integer. But root n is not integer. So once you make the substitution, the flooring also goes off. Okay. Then log n is equal to m. So now the size of the input is m, not n, because of the substitution. Now, again, this is the power is having m by 2, but it is not like m minus 1, m minus 2 like that. So we have to bring it to that particular format once again. So once again we are making substitution. Let f of m is equal, m is equal to T of 2 power m. Then what happens? This becomes f of m equal to 2 times f of m by 2. So whatever is in the power, that is going to come here, right? F of m by 2 plus this m, right? So here only change, but variable is not changed. Therefore, this m comes like that. Okay, now you see this is something similar to the recurrence equation of merge sort that we have seen already, right? F of n is equal to 2 times f n by 2 plus n like that. It's similar. So how to solve this? We have already solved it, right? So we can write the complexity straight away. So this is equal to order of what? M log m. Order of m log m, right? Because this type of recurrence equation we have seen earlier, and we had the answer, right? So that answer we write it straight away. But size of the input is m. But what happens? M is not our original size of the input, that is n. So again we have to substitute back. So what you substitute back? M is equal to log n, right? M is equal to log n. So if you substitute that, that is order of log n. This is log n. So this is the final complexity. So order of log n is the complexity of this recurrence equations.